Yeah. Hi, good morning, everyone. So I'm going to talk about these MHD simulations through this magnetofrictional approach. So actually, this work was started around a couple of years back when I was visiting Nodita. So during that time, I was taking help from John Warnke and Philip Bodin and including Excel also. But still, this work is not fully completed because I took help from them. So for whatever the existing modules are there with pencil code, so I put them as my collaborators. I hope they have no problem with that. So coming to the talk, so the main interest is that the active regions of the solar on the sun. So if you see on the sun, generally the active regions do emerge in a time scale of days. Here you can see, you can follow my cursor. See, the active regions do emerge. While emerging, they do spread in area with uh, with their motions. Either it is shear motions or it is separating motions. So that is the major thing that the all the large scale activity, including flares and CMEs, which are mostly happening from this the regions called active regions, which have the very strong magnetic field. So, so the major process when these active regions do emerge is that this is the photospheric flux emergence, which is something due to the vertical motions, that is from beneath the sun, and also on the surface there is a more slow photospheric motions, that is on the surface horizontal motions. It could share motions or separating motions, whatever. So in order to study these flares and CMEs, we do follow the active regions like this. So here the active regions emerging on the full disk. So we track that active region in the localized region like this, and we arrest that, and in time we follow that active region. So the images what I show here, the animation, which is the line of sight magnetic field evolution taken from HMI. So that was our interest is that using these magnetic field observations, which are available at every time instance continuously over 24 hours, either it is a few minutes to or hours. So we can use these observations to model the magnetic field. So which is very important to understand the magnetic eruptions, which are CMEs and flares. So that was our intention to do this all these simulations and models, all these things. So here is one example that how large scale eruptions can happen. So here on the disk, which is AIA 131 observations. So there is active region called uh, it is the active region number, if I forgot, 12673, I think. Yes. So it gives the very largest layer x 9.3. So followed by there is a large CME which is going through along the near the disk in the along the limb direction. Okay. So there is a then we do observe in the X-ray observations that there is a light curve. So that points to 9 in the X-ray scale. It goes to more than X10 class flare, which was the largest flare according to 24 solar cycle. So that also coming to the data-driven simulations. So we have the initial field, which is coming from model in the solar atmosphere above the active region, and the boundary is time varying. So if you keep varying, changing the boundary from the observations of the magnetic field, then how do the coronal magnetic structure do evolve, and that evolving magnetic structure can explain the magnetic eruptions. That is our aim. So this is the basic understanding. So what is the to tell about the data driven simulations. So the aim of these data driven simulations, especially in the context of sun, is that the small scale and large scale. So in the small scale, which is something more important, is the coronal heating. So there we study the full MHD equations. With the help of full MHD equations, we do keep changing the bottom boundary and try to understand how the corona is getting heated by. So in the previous talk, Bodin has given one talk. So probably that belongs to this class of simulations. So other class of simulations which I'm interested and I'm going to discuss in this case in the large scale active regions. So to understand the flares and CMEs. So please try to understand that the time scales in the coronal heating problems, the time scales could be few minutes to a couple of hours or like that. In the large scale eruptions, the energy storing time scales and eruptions are, it could be days. So these are two different things. So also understand that in the later case, the only magnetic field is the main driver. So that is the major source of energy. That was the main point to note. So the basic MHD equations which we use, no need to tell much on this, is that these are the equations which I use, but which can be solved through pencil code. Coming to Magneto-friction relaxation, so we don't use all these equations in the Magneto-friction. We use only the force balance equation, which is here written in the equation of motion or force balance equation. So there the dissipative term, which is dV, which is in the earlier case, which is coming from the viscous dissipation. So here the velocity is the frictional term, that is dissipative term, is proportional to velocity, which is written. The first was proposed by Young in 1986, and later some people applied to the solar active regions. So in the magnetostatic conditions, this equation yields to give the velocity, which is Magneto-friction velocity, written like this. So which we substitute into the again induction equation. So that gives the this form of the induction equation, including resistivity and the Magneto-friction coefficient mu. Okay, so we have to choose both mu and the mu such that the velocities are approximately the same as the observed case in the sun. So that I will come in later. So this is the implementation in the pencil code. I implemented this Magneto-friction, this equation, the last equation, in the magnetic.f9 module, which is located in the source SRC directory. So here two things I implemented, because the velocities cannot be, while magnetic fields are very small in the denominator, so sometimes this velocity shoots up, that may goes to several orders. In that case, our time steps may become very smaller. So to arrest that, we put a cap on these velocities, the Magneto-friction velocities, which is up to 40 kilometers. And also because we are moving the bottom boundary, so because of that, velocities are also coming from the change of the boundaries. So in order to stop that, we put some condition such that the velocities are 0 at the bottom boundary, and it keeps growing while we go upwards in the atmosphere. So that is a condition we implemented in the Z direction. So so that the moving boundary, the change of the boundary does not come into the effect as the magnetic friction velocity. So this is the implementation. And so coming to the make file, we don't need to use any other modules except the magnetic module. So you can see here magnetic module only used, nothing else. And we need initial conditions, the FFT module, which is Fourier FFT pack, that we use in this case, nothing else. So coming to initial condition, so because as I said that we are working with observations, so everything is magnetic field observations, whereas pencil code works in the vector potential. So we need to convert all observations into vector potential. So for that, we don't have any analytical expression for that. So we need to work on this particular gauge. In this case, we use the Coulomb gauge. So using the Coulomb gauge, the vector potential for vector initial potential vector potential AP is given by this expression. Of course, this is Green's function approximation. In this case, you using the initial magnetic field BZ component of magnetic field at the boundary. So we can construct the vector potential by this equation. In the pencil code, it is done by the FFT module. So through Fourier transform conditions. So that is given in the manual already. So if it is the case for potential magnetic field potential magnetic field model. So if it is not the case, for example, the magnetic field is highly twisted in the solar atmosphere, in that case we need to do some kind of extrapolations which is coming from some other models and other numerical techniques. So if you do that, in that case we can construct under the Bloom case the vector potential A with this expression. So here B is coming from the given model, either nonlinear force field or linear force field approximations. So these two are we can use as the initial condition. So yeah. So coming to the boundary conditions, given the BG component at the surface, we construct the vector potential AP by this Fourier transform at each time step, while the time step is also interpolated between two observations. So we can use this Coulomb case condition. So in this case, we contain only two components of vector potential. So anyway, that is okay. So boundary conditions are in our case, we use two runs. Okay, we can do two runs. So as I said, from this expression, that is a vector potential, you can get two cases. One is a vector potential at the boundary A is equal to potential magnetic field AP, which is purely depending on the BZ component. Other thing is that it is either another module, either linear force field or nonlinear force field. So in the linear force field approximation, we have the only some average speed which is going into the atmosphere, and the nonlinear force field it is spatially varying. So in this case, the assumption, the way it is constructed, the vector potential for a given model is that the BZ component is same for both potential field and the nonlinear force field or current carrying field. So given this kind of information, I apply to the solar active region 111429. So this please note that this is very preliminary results. I found some difficulties, so which I will explain while showing the results. So this solar active region 111429 is highly eruptive active region. While it is passing through the on-site disk, it has produced the three M-class flares, one X-class flare and two M-class flares, followed by CMEs. So these are the observations, electromagnetic field observations of this active region. So you can see there is a polarity inversion line. While this active region evolves, the opposite polarities have shared motions with respect to each other. So that builds the magnetic share, so such that the horizontal magnetic field along the polarity inversion line will be parallel to each other and parallel to each other. So that is a very nice condition to have a energized magnetic system along the polarity inversion line that do produce the flux lobes, and these flux lobes sometimes they may come across the instability and they may erupt at some point of time. So our aim is using these time dependent boundary conditions. We drive the initial condition, that is the solar atmospheric magnetic field, which is a potential field and linear force field, and whether that can give rise to an eruption or not. That was our aim. So the important thing, as I said, that so we have to somehow in the observations of the magnetic field, which is the twist is embedded in the transverse magnetic field components, that somehow we have to embed into the vector potential APA that goes into the model in simulation. Okay, so that is the one important difficulty we found here, such that the twist information can be injected into the atmosphere. and so that we can get the twisted structures in the atmosphere. So the simulation runs, the computational blocks is actual solar observations, and that spans up to 279 megameters, and we made it the zero minus that 139 to plus 139, such that the dimensions are the extents of the box dimensions are 1279 megameters. So we use the periodic boundary conditions in the horizontal direction and the extrapolation boundary condition in the z direction. So as I said, there are three feasible runs that we can do, such that we can get the more twisted structures in the solar atmosphere. So as you go from 1 to 3 runs. So here I am mentioning the only in terms of magnetic field. So we all work in the vector potential when we work on the code. So one is the driver field is Vz, and initial field is potential magnetic field. Another is driver field is linear field, so where we can embed the twist in the magnetic field, so that goes into the solar atmosphere, which is initial condition as potential magnetic field. And the third one is that the initial field is non-linear force field, which is already highly twisted structure, which is very which resembles the coronal magnetic field as observations, and that again we drive with the linear force field. Okay, so these three runs we can do. So in this case, in this presentation, I present only the first two runs. So let me run this just animation. That so as you see that so that each time here I run for 3 days this entire run by the run number 1. So each time 1, 2, 3 like that corresponds to half an hour time, actual time. So as you see, you start with the potential field, and while you keep changing the boundary, the coronal field it evolves, and slightly it becomes the shared structure, okay, in the corona, like a inverse S shape. Okay, that is very slight visibility. You can see this. Okay, so this is the animation, and also you can notice very slowly the loops become closed, and you can see here the first shape loops forms uh, at the extreme ends. So that is a signature of the reconnection, usage of the diffusion, okay, especially. And coming to some metrics, so in this case the AB int, that is the A dot B. So it is while you keep changing the boundary, and anyway the coronal magnetic field accumulates the helicity, so that the A dot B increases in negative values. So please note that helicity is a plus or it is a quantity, definite quantity of plus or minus values. So plus sign is a positive chirality. That means that it has a forward S shape, and minus signs refers to inverse S shape. This is a typical notion which we typically see in the solar observations. So this is very fine because we drive the boundary with the simple potential field, and because of this shear motions only, this buildup of the coronal helicity happens. This is somewhat reasonable, as you see. And also because A dot B we calculated, and here relative helicity, which is A plus AP, and relative helicity is something it gives the information about the excess magnetic twist above the potential field. So that also is same, because in this case the A dot B is not very much different, because we use the only Coulomb gauge condition. Coming to energies, here you can see the difference in energies, which is free energy, which is approximately 1 into 10 power 32. Is a typical energy to power the ANX class and M class player. So coming to the second run, which is where the twist information is going in. So let me show the simulation. We can see here the field lines are, the topology is highly shared, and you can see more sigmoidal structure than the earlier case. Okay, now you can see, I can stop now. So I can stop now. So this is a more sigmoidal in shape, okay, inverse S shape. Okay, but whereas the highly twisted structure should form along the polarity inversion line in between, which is the core magnetic field, but which is not the case because the twist information is not properly embedded inside, going into the corona. So this difference is clearly exists because both the first run and the second run, we see the difference very nicely, but it is not sufficient to give an eruption, large scale eruption, which is not seen here. So coming to the metrics, the coronal helicity is 100 times more than the earlier case. Okay, so A dot B values here. So it is of the order of approximately some 6 values, whereas in the earlier case it is 0.2 something like that, and an average. So this means that it could be of the order of some one order. So it's higher values, but even then also we don't see a very significant twisted structures, especially in the core at the core of the active region. So that was my concern. Whereas the magnetic energy also little higher compared to earlier. Okay, so it is above on an average above 1 into 10 power 32 orders.
Vema, you have 5 minutes.
Yes, I'm already done. So let me point out my concern that in run 1 and run 2, we found the difference that, so there is a significant difference in the field topology. There is no significant difference in the field topology. Even there is a difference in A dot B values. Okay, it is here you can see here and there. It is of the order of some 10, 20 like that. Sorry, by multiples of 10, 20. Even then also there is no significant difference in the field topology. That was my concern. I'm still working on it. So run number 3 is still yet to be performed because I encountered difficulty how to convert the non-linear force field, which is coming from other techniques, to vector potential A. That is a big thing, but which was not successful. So this is the field topology coming from non-linear force field. We can see highly shared. Inverse sigmoid structure is there, and we can see in the core of the magnetic field is a form of a twisted structure near to the like a flux rope here. So at the follow my cursor. So thus a similar structure is almost we can notice here while in the run number 2. Okay, run number 2 after certain time, but it is not to that extent. Okay, it is not to that extent. It is almost is there like this, but the core field is not that highly twisted. So that was the problem. Still we need to pump the magnetic helicity, the twist information from the boundary into the atmosphere, such that twisted structures do form in the simulation. So that I am still working on. If okay, so coming to so this is my last slide. So reproducing twisted structures is more important so that we can use them as initial condition for full MHD simulations. So that is one of the main important aim. So still I need to work on run number 3 because we need to write the initial field as vector potential. We found some difficulty to understand the no much difference in the field topology. Okay, even if there is a significant volume magnetic helicity. We need to apply to other activities also, and of course, so global magnetic field evolution also we can, if it is succeeded, we can also work on the global magnetic evolution. Like So we need to use a Carrington maps in that case. So given all these things, we can also work on the full MHD setup, such as taking this MHD, this vector potential run as initial condition, and they use full MHD to study the dynamical evolution during a flare or CME, including the reconnection and the particle heating. All these things we can do that. So that's all we can present.
Okay, thanks, Vema, for your talk. We have time for a few questions. So please go ahead and raise your hand. Yeah, John.
Hi, thank you for your nice talk, and thank you for working on it, even though we haven't really, or I haven't really helped you much in the last
yeah, it's okay, no problem. No problem.
Yeah, so we should keep it up. So maybe we should have a next week or something. We should have
yeah, sure.
Have a Skype meeting or something. So I have two questions. So first question is, when you do the non-linear force-free extrapolation, or even the linear force-free extrapolation, when you look at the equations, I think you had some slide. Don't you assume there is a certain gauge already? And does this conflict that you have to choose also a gauge for the pencil code? No.
So when you do linear or non-linear force extrapolation, there is no gauge we impose. Okay, it is directly we work on the magnetic field observations. Okay, so that is a kind of some relaxation techniques which some other people do use. So there is no gauge we need to impose.
Oh, okay. I don't know. And then I was a bit one question about your three basic runs. So I understand the initial field, but so your driver field, but shouldn't be the driver field the same as the initial field? So that's a risk you confuse.
No. So my intention is that if the initial field is already twisted, okay, so our driver field is further twisted as much as that. Okay, in that case, we keep that structure, the coronal topology, same as that, and so that it will relax from there onwards. Okay. So otherwise, if the driver field is less energetic than the already existing structure, then it will relax to a lower energy state. Okay, so that's what only the thing which goes into coronal volume is that the boundary motions. Okay,
but the difference between your run 1 and 2 is basically that you also have not just the BZ but also a horizontal field in the photosphere. Is this one of the difference?
In the run number 1, okay, run number 2, okay. So let me, okay, here. So, so in this case, I use the linear force field. Okay, what I did is that, so I constructed linear force field from alpha. Alpha is a condition coming from the horizontal magnetic field. Okay, so that information I use that such that it could be the driver field is little more energetic than the initial field. So that's why you see the higher magnetic energy and the coronal helicity also, A dot B.
No, but I mean technically that you have also horizontal components in your boundary in your field at the boundary.
Yes, it has gone in the form of alpha, a parameter.
Yes.
Right.
Good. Yeah, thank you for now. Let's keep in touch. Yeah.
Right. Yes.
Next question by Dhruva.
Hi, this is Dhruva.
Yes.
What I am my question is more about the fundamental nature of the work.
Yes.
So you have an active region and you are trying to see how the field of the active region evolves, but your code works in a certain resolution. Your active region data is measured at a certain resolution.
Right.
Your code uses some parameters of viscosity, magnetic diffusivity, and so on.
Yes.
The sun may have something else. So how do you translate between these? Or if you translate only some and do not translate the others in a similar way, then maybe you may get some inconsistencies. Do you see what I mean?
Yes, I understand. So exactly, I'm saying that what I want to say that the active regions are strongly magnetic field. So there is no point that the other terms like viscosity, plasma, and other things, they do have a role in the buildup of magnetic energy in the such a large scale magnetic structure. That is one point. Okay, so that's why I work on the only magnetic fields only. Number 2 point is that regarding the resolution, of course, that do have some role. Okay, in this case, we reduce the scales to a factor of 5, such that we can, because we are working on long time scales of the order of 3 to 4 days, it is not possible to work on the actual scales, which are, it takes a lot of volume and time also. So even then also, we need to see what exactly we are supposed to. So that is our aim. Of course, that do affect the loss of resolution, that has some concerns, especially the small scale twisted structures we may lose. Okay, but by and large, we should get the topology same as this. That's what you see in the both of these things. So in this NLFF extrapolation, we see very clear the at the core of the active region, you can see twisted structures, whereas we lost them in the simulations. Okay, here. So that is, those things are due to the resolution, some sort of resolution. So probably I can increase by a factor of 2 resolution. Then we can reproduce that by somehow. Yeah, my something reasonable I answered you.
You have a magnetic friction parameter, right?
Right.
So that is also an, I mean, you may not have viscosity, but you have magnetic friction, which you don't know.
Right. So our main thing is that only magnetic field. So Lorentz force is the only.
I understand, but you also have to put a friction term.
Friction term means we keep the, okay. You need to keep. So in that case, we need to work with the plasma. That takes more time consuming. Okay. So
let me just mention a word. Maybe that will help orient in the direction that I am trying to go.
Yes.
So there is a thing called data assimilation. You see the people who, for example, look at satellite pictures,
right,
and then tries to see whether a hurricane is going to happen or not. Like, I guess in the Bay of Bengal now, we have a cyclone that is moving.
Yes.
So what they do is a proper translation between the measured quantities and the code quantities. And it's a technique called data assimilation, which translate this in a least square sense. So I was wondering if that is important here or not, but I guess it will be a longer discussion.
Okay.
Yeah, I think we are sort of running short on time, so better to continue this discussion on Slack. So I think we'll move ahead with the next talk, which is again by Dhruva, who will be speaking on.
Just Philip has his hand raised.
Okay.
Yeah, I know. Okay, so.
Okay.
Okay, fine.
Fine. Okay, no problem. Philip, you can go ahead.
If you can hear me well.
Yes.
So in principle, it would be possible to compute also currents from your magnetic field, right?
Yes, I can do that.
That would be also interesting to look at what is the current density in the volume, or even maybe as a global quantity like the sum, because it would also describe what is the amount of magnetic energy that is dissipated.
Okay.
So maybe that we could look at.
Okay, I can look into it. Okay. Thank you.